Now, so today, getting to the next section of polynomial interpolation, we've seen two ways of obtaining the interpolating polynomial. One is by solving a system of linear equations, the van der Waals matrix. That's the awful method. Then there's Lagrange, which we saw last time, and now today, or this week, Newton interpolation. I think I budgeted 2 whole class days for this section. Then when I looked at my notes from last time, I think 2021, I ended up covering it all in one day, which might not have been the best idea, but we'll see how long it takes. But what that means is that any other class time we have, like Thursday, is for homework questions. Okay, first I want to talk about the upcoming midterm. So, okay, you'll look at Canvas. So down here I have the midterm is going to be a take-home, and I'll talk about the time frame for that in a moment. But it actually was something I was given in class like before a pandemic, and then I just never bothered changing it back. So there's a practice that gives you an idea of what kind of problems the midterm will have, and there's a solution. So you can look at those at any time. And I suggest you do to have an idea of what you're in for. Now, as for the format, so there's going to be 2 parts to the midterm. First, so 5, I'm calling regular problems, like you'll see in a practice. I guess you consider kind of exploration like, and those will be worth 10 points each. There's no MATLAB involved in this. So this is the sort of thing that can be done on paper. And then the other part is 10 questions that are concept check like. Those will be 5 points each. Now, the coverage of the midterm as a whole, both parts, is starting from section 2.1, that's on error analysis, convergence, that sort of thing, up to 7.3, the section that I'm starting today. Now, I want to say something about how this relates to the homeworks. Right, here are all the homeworks. So the midterm deals with, okay, homework 2, 3, 4, that take you up to 7.2. Now, and the first half of 7.3. Now, this homework is not due until later. It'll take some time because of midterm and fall break before I cover 7.4, and that is not part of the midterm. Now,
7.3 is.
Yeah, although actually, if I look at the problems for 7.3, I believe both of these are MATLAB problems, which are not relevant to the midterm anyway. So even though midterm coverage dips into homework 5, you don't need to do homework 5 to be ready for a midterm. You can look at whatever practice problem you see here. That is what you want to look at. Okay. And I'll be able to tell you what kind of problem that from this section is going to show up in the midterm by what you see today. Okay. Now, time frame. So by 5:30 p.m. on Wednesday, October 4th, is when the document will be posted in Canvas and also on my own site. That's when you can get started. And then it'll be a Canvas upload, just like the homeworks are, by this time. the following Friday, October 6th. So you have a grand total of 54 hours and 29 minutes to get it done, to complete the mission. Okay. Now the practice that I posted in Canvas only includes problems for this part, like the regular problems. Reason why is that the study for the other part, look at the concept checks, look at the quizzes. Those are the kind of questions you can expect. Speaking of the concept check or quizzes, they're meant to be based on the reading. And then oftentimes the answers are kind of given away there. So make sure to do that on each section that's covered. You know, it can be painful. It's reading math generally is. Okay. Okay, so as I mentioned, apparently I've budgeted too much time this week, more than what I need to cover this next section, 7.3. So Thursday, in particular, will be a great day for any of you to raise homework questions, because they'll have all the time in the world. So don't waste it. Speaking of homeworks, like 5 or 6 people or so have turned in homework 2. That's not quite half the class. Once I get a few more turning that in, then I'll read whatever's there. Same thing with one of the quizzes. I think like 5 or 6 people have turned that in. So I try to wait till there's like a critical mass, and then just plow through them all. Okay, so any questions about what I've just been talking about? Yeah.
So are for those who have turned in whatever assignments haven't been graded yet, will those at least the ones that are for that apply to the sections that are going to come from midterm?
Okay, I'll catch up on. I'll do my best to catch up on whatever I have received by that time.
Like before the midterm?
Yeah.
Okay.
I may not be able to catch up on everything, but yeah.
Okay.
Okay. Well, and I think we've only had one submission on homework 3, so. Okay. But yeah, your best tools for preparing are the practice thing that I put out and then the quiz questions. I'll certainly make sure to get the quizzes. Those are relatively quick anyway. You have a question? Okay. All right, so yet another way to produce the same interpolating polynomial that we've already seen, but still with some advantages. So, as a recap, this is a problem that we're trying to solve, that we're given n+1 points in the plane, so x coordinates and y coordinates. We are assuming that the x values are distinct. We're actually going to drop that assumption later on in this chapter, but for now we're going to assume they're distinct. And what we've done so far is rely on this assumption that the x's are distinct. And we're trying to find a polynomial Pn of x, the degree n most n, that satisfies these conditions that you plug in each x value to get the corresponding y value. Okay, so that's our generic polynomial interpolation problem. And just to recap the approaches that we've seen so far. So first, we're obtaining the polynomial in power form. So the most customary way of representing a polynomial with coefficients times the power of x. And you substitute in each x value in here, set that equal to the corresponding y value, and you get a system of n+1 linear equations in n+1 unknowns that are for coefficients, a0, a1, a2, etc. And you just solve that system. The matrix of that system is called a van der Waals matrix. And as I mentioned before, a couple of drawbacks to that approach. This is more expensive than necessary, or n cubed floating point arithmetic operations. We can do better than that. N squared is possible. Also, if the x values happen to be clustered closely together, this is the system of equations to solve is ill-conditioned, which could lead to undue errors in the results. So we didn't really bother with this one. The second approach that I covered last time, Lagrange interpolation. So here we have a different form of the interpolating polynomial. The polynomials themselves are the same. Like if you were to expand all of this out and match the coefficients, they would be the same. So now the coefficients of this linear combination of polynomials are just the y values that you're given in the first place, these y's here. And then I described how to get Lagrange polynomials last time. They have a property that if you plug in xi into the jth Lagrange polynomial, you get 1 if I equals j, 0 otherwise. So it's possible to form the polynomial Lagrange form in or in squared operations. But evaluating polynomial at a given x, that could be expensive because these polynomials are have much more complicated expressions than these monomials here. And that's why I introduced barycentric interpolation as a more efficient way to evaluate the Lagrange interpolated polynomial. Okay, so all that is just a recap of from last time. Okay. Now, one drawback of the Lagrange approach, and it actually applies to the first approach too. Suppose you've gone ahead and constructed Pn of x in whatever form, and then you decide that you needed to include more data. You want to use a higher degree interpolating polynomial to account for adding a new data point. Every time you add a new data point, that bumps up a degree of your polynomial by 1. Well, if that happens, all the Lagrange polynomials have to be changed. So it takes there's no convenient way to update this polynomial when to account for new data. You have to start from scratch. Same is true here. Your system of equations, the matrix can be updated, but solving a system is still a whole lot of work. So another way of phrasing it is that Lagrange interpolation is not progressive. Progressive in this case means that it's easy to extend your solution when you add more data. So it's not easy to do in this case. So that's why we're still on this topic. That's why I'm showing you yet another polynomial interpolation method, Newton interpolation. It's one that can be updated to account for the data. Okay, so now we're going to have a third form of this Pn of x called Newton form. At first glance, it looks kind of like Lagrange form. We have Pn of x is some linear combination of some coefficients times these polynomials that I'm labeling as, I guess, fancy n sub j of x. So I need to explain what these are. Okay, so that'll be on the next page. Okay, so these polynomials, the subscript indicates the degree of each polynomial. So n0 of x is just a constant, it's just 1. n1 will be a factor x minus x naught, so just a linear factor, degree 1. And notice what happens as I go from each one of these to the next. I keep whatever linear factors were already being multiplied, and I just tack on a new one. Until finally, like this one has x minus x naught, x minus x1, x minus x2, and so forth, all the way up to x minus x sub j minus 1, so that the whole thing, nj of x, has degree j for each index j. So now what I have to do is by defining these polynomials, n0, n1, n2, etc., I have to solve a system of linear equations basically to get these coefficients, the Cj. But what happens is the matrix involved in solving the system is what's called a lower triangular matrix. So a lower triangular matrix is the matrix in which every entry above the main diagonal is 0. Those kind of systems of linear equations are relatively easy to solve. Can be solved in order n squared operation, floating point operations. And that distinguishes from the first approach that I showed you, solving system equations based on this. When I showed you that van der Waals matrix from last time, every entry of that matrix pretty much is non-zero. So it's a full matrix, and that takes order n cubed operations to solve. Whereas if a matrix is lower triangular or upper triangular, what you knew of in that 326 as in being in row echelon form, that takes only order n squared operations, so it's much more efficient. So what I'm going to show you is a relatively simple approach for computing all of these coefficients in the Newton form. So what these coefficients are called, they're called divided differences. And the way they are described is if I'm approximating a function y equals f of x by my interpolating polynomial, Pn. The divided differences are denoted using the letter of your function, f, and then square brackets, and then selected x values are listed inside the square brackets. So I need to show you how these divided differences are defined. They're defined recursively. So what we have here is, they call it a zero-order divided difference. So each one of these has only one x value inside the square brackets. So f square bracket xj is the same as just f of xj. I mean, I'm evaluating the function at xj, and that would be yj. So the simplest divided differences, these right here, they're just the y values. Then I come to here. These are called the first order divided differences. Notice that in the square brackets you have two x values listed. And the way I compute it is we have this difference quotient. And can anyone tell me what this resembles? This kind of difference quotient? What it might remind you of?
Limit.
What?
Oh, derivative.
Yes, derivative. Yeah, it's that by the mean value theorem, this is equal to a derivative at a point in between. So yeah, it's a difference of f values divided by a difference in the corresponding x values. And this is where the name divided difference comes from. Okay. Now I go to the next, a second order divided difference that has three x values listed here. And watch what happens when I show you how it's computed over here. Because the three x values I have listed are xj, xj plus 1, xj plus 2. So here I have two of those values, xj plus 1, xj plus 2. And then over here I have f with the other two other x values, xj, xj plus 1. And then so this difference is divided by the difference of two x values. Now, which two x values? Notice that what we have here, these are two first order divided differences. And I'm subtracting them and divided by difference of x values to get a second order divided difference. Notice they have one x value in common, xj plus 1. That is the x value that is not included in the difference down here. It's the x values that these first order divided differences do not have in common that are subtracted down here. So what we're seeing is a higher order divided difference is obtained using a difference of lower order divided differences divided by a difference of x values. So there's a whole lot of differencing and dividing going on. In general, this is a general formula right here for a divided difference. That here we have a divided difference of order k is defined by subtracting divided differences of order k minus 1 and then dividing by a difference of x values. So the x values listed here and here are largely the same. The difference is this one does not include xj plus k, and this one does not include x sub j. And those are the x values that are subtracted below. Now, these can be pretty difficult to understand just from the definition that I've shown you here. But what I'll be doing is showing you how you can compute these without too much difficulty. It's a matter of how you keep track of everything. But I'll come to that momentarily. But once you have computed all these divided differences, these right here, then you can form the Newton interpolating polynomial. You start out with a zero order divided difference, your constant term, so f of x naught. And then watch what happens when I go to the next term. I have a higher order, first order divided difference, so x naught and x1. And then I multiply that by this linear factor, x minus x naught. So that's my first degree term. Then I have the next term, I have a second order divided difference, x naught, x1, x2. So each time a new x value is added to a divided difference, and then I include a new linear factor when I'm multiplying here. I have x minus x naught times x minus x1. And I just keep going. I keep going to higher order divided differences, using the same points as before, adding on a new one. And then with each term, I'm multiplying by whatever linear factors I had multiplied before and tacking on a new one, like this one and this one. And so you build up the Newton form one term at a time, each term having degree 1 higher than the last, until you're up to degree n. So it turns out that in describing this Pn of x, I've actually given more than that. This first term right here, that's P0 of x, and interpolates at x naught. The first two terms are P1 of x, that interpolates at x naught and x1. First three terms are P2 of x, a second degree polynomial, that interpolates at x naught, x1, x2. So every time I add on a new term, I'm getting a new interpolating polynomial that accounts for one more point. So this form of the interpolating polynomial, unlike the other two, is progressive. So if I want to include a new point, xn plus 1, so now I'm going up to degree n plus 1, what I would do is I would take all of this and add on just this one new term. So the Newton form is the only one that is very easy to update, in that if you're just adding on one more interpolation point, you keep everything that you had before, you're just adding this onto it. Any questions so far about the Newton form? Okay. So here's how everything, all this actually gets worked out. It involves completing what's called a divided difference table, where you keep track of all the divided differences needed to get the ones you actually need. And this most easily described using an example. So in this example, this is a sample data that I've used before. Here we have 4 interpolation points, x0, x1, x2, x3, that are equal to -1, 0, 1, and 2. Here are corresponding y values. F of x0 is 3, f of x1 is -4, then 5, and -6. So how you start a divided difference table is first you list your x values, x0, x1, x2, x3. And then you list your y values. Okay, so in this case 3, -4, 5, -6. And then what you do is to get the next first order divided differences in this third column here. Notice I've written these between the divided differences from a previous column. Because as we go from to higher order divided differences, we have fewer of them. So how do I get this one? I take -4 -3 divided by 0 minus and -1. So it's -7 divided by 1, so I get -7. So each divided difference comes from subtracting the 2 that are immediately to its left, and then dividing by differences of the corresponding x values. So like for this next one here, I have 5, this one is equal to 5 minus a -4 divided by 1 minus 0, so it gives me 9. And then I have one more, -6 minus 5 divided by 2 minus 1 is -11. So that's how I complete this next column. And actually, I want to see if I have something more detailed. Oops. In the text. I don't have this example in there. Okay, yeah, this is involving the same data. Okay, yeah, so here it's the same divided difference table, but it's more written out in a more detailed manner. So for instance, if I, like here, I want these next divided differences. So x1, x1, x2, and for that, I'm computing that up here. So I'm going to take 9 minus a -7, and then the x values that I'll subtract. So it's divided. Okay, actually, yeah. So 9 minus -7 But as far as the x values are concerned, I'm going to take x2 minus x naught. Because these two divided differences, they have x1 in common. But if you divide by the difference of x values that they don't share, so x2 minus x naught. Similarly, if get this divided difference here, I have minus 11 minus 9 divided by x3 minus x1, so 2 minus 0, and that gives me minus 10. And that's what you see here. And then finally, for the last divided difference, way out here, f of x naught, x1, x2, x3, I take the one immediately to its left, so minus 10, minus 8, and then that's divided by the difference of the 2x values they don't have in common. Notice they share x1 and x2, so you're going to divide this by x3 minus x naught, so divided by 2 minus 1, and that gives you minus 6. You can see all the details here, as far as how the individual entries were computed. But it's always a difference of adjacent divided differences of the order 1 less, divided by the difference of the x values that you don't have in common. So like in this case, because this one features x3, and then the one above it features x naught, that's why it's divided by x3 minus x naught in that order. Are there any questions about how the divided difference table is filled in? This actually will be one of the midterm problems. And you'll see that in the practice, where you're given some data like this, and then the problem is to fill in the divided difference table. And then once you have done that, then you take the coefficients from the top row of a divided difference table. So in this case, the 3, the minus 7, the 8, and the minus 6. And what you do is you write down the Newton form as follows. So first coefficient, the 3, that's by itself. And then you have plus minus 7, the second coefficient, times x minus x naught. So it's x minus the top x value. Then plus the next coefficient, that's the 8. And then whatever linear factors you had in the previous term, you carry over to the next term, and you'll multiply by a new one. So it'd be x minus x1. And then finally the last coefficient, the minus 6, times whatever factors you had before, times x minus the next point, x minus x2. So although we're interpolating at x0, x1, x2, x3, you notice that x3 doesn't actually show itself in the Newton form, but it still has an impact because the value of x3 played a role in computing some of these divided differences. That's why it's still relevant, even though you don't see it actually listed here. And then you're done. You have the Newton form completed. Although it's not unique. Here I showed you, in this case, using the top row of the divided difference table, but you don't have to. There's more than one way. You can also use the bottom row of a divided difference table. You're just multiplying by different linear factors. So the bottom row I have minus 6, minus 11, minus 10, and minus 6. So I have minus 6 by itself, and then I add on minus 11. But notice the linear factor is different because I'm starting from the bottom. So I have x times x minus x3. and then I go to the next coefficient minus 10, and I keep the x minus x3 multiplied by x minus x2, and so on. You see, it's important to see the pattern of what these factors are. So here I'm going through points in order from first to last. Here I'm going through points in order from last to first when I'm using the bottom row. Polynomial produce, like if you were to multiply all these out and combine like terms and all that, they'd be the same. They're just represented differently. Okay. Any questions about how you build up a Newton form? Now, once you have a Newton form, we want to be able to evaluate it efficiently, because this was an issue with Lagrange interpolation. Lagrange form is tedious and it's computationally expensive to evaluate, and that's why barycentric interpolation was developed. It turns out the Newton form is more efficient to evaluate if you go about it carefully. Now, the idea is this. So here's the first form, the Newton form from up above. What you can do is, if you note that, for instance, all of these terms here that I've highlighted have x minus x naught as a common factor. So I can factor it out of them. Then, I have what's left, I have minus 7, and then these two terms not only share x minus x naught, they share x minus x1 too. So I factor that out. So what I have is, this is written in what's called nested form. So what you do is, first you compute x minus x2, whatever x you have, multiply by minus 6, add an 8, then you multiply all of that by x minus x1, add on minus 7, then multiply all of that by x minus x naught, and then you add on 3. So here's the way you would actually evaluate it. So you start with y equal to your highest degree coefficient, multiply by x minus the interpolation point, x minus x2. Add on the next coefficient, multiplied by another linear factor. Add on the next coefficient, multiplied by another linear factor. So you see that the divided differences are added on to y in reverse order to how they were listed here. So notice for a degree 3 polynomial, there are only 3 multiplications, here, here, and here. And then there are 1, 2, 3, a total of 6 additions. So for a degree n polynomial, order n operations are needed to evaluate it. That's really the best you can hope for. Whereas with Lagrange form, unless you use barycentric interpolation, order n squared is operations are needed. I want to point out that for a polynomial in ordinary power form, if you were going to evaluate this, you have to be careful about how you do it, because after you compute x squared, you don't want to compute x cubed from scratch. You should take your x squared from before and just multiply it by another x. To perform as few arithmetic operations as possible. And that is what is accomplished using what's called Horner's method. So here's a polynomial in power form, the cubic. And I use the same principle, that after I separate a naught, all these other terms have x as a common factor. So I factor out the x. And so on. So here we have the Horner's method for evaluating a polynomial in power form again, for whatever degree you have, n, it requires this n multiplications. It also requires 1, 2, 3, n additions. So using Horner's method with power form, that's the most efficient way to evaluate polynomials. So degree n, n multiplications, n additions. For a polynomial in Newton form, the idea is similar. It's just that now each of your x's is shifted by one of the x values of your interpolation points. So that's why it requires more additions, but the number of multiplications is the same. When you're counting how many operations you need to carry out a computation, it's important to note that multiplication and division are significantly more costly than addition and subtraction. And the reason why is, think about how you first learned to do addition. You had, like in elementary school, when you had to do numbers of however many digits written out, and you're adding and multiplying them by hand. That with addition, you just line up the digits and you add it. And if you're adding two numbers with n digits, it takes order n amount of work. Whereas in multiplication, every digit of the two numbers you're multiplying interacts with every other digit. So if you're multiplying two digits, there's two n-digit numbers, that takes order n squared work. So multiplication is far more expensive, and division is the most expensive arithmetic operation of all to implement it in hardware. So if there's a way to modify how an algorithm is implemented to reduce the number of multiplications, even if that means using more additions or subtractions, that's generally an advantage. So the fact that the number of multiplications is kept at a minimum is particularly important. And the thing is, it's easy to think, oh, computers are so fast these days, does it really matter about polynomials? Yeah, but look how many operations computers are expected to perform now. And gazillions, because yes, they're getting more powerful, but it also means we're demanding more of them. And the thing is, unfortunately, because it's possible to do so many things related to programming so quickly, it's led the current generation of programmers to be a lot less careful than it used to be. And so to explain what I mean, so this is a story that I heard secondhand about where my undergrad school, Purdue, I heard a story about what it was like for researchers at Purdue in like in computer science or mathematics, really, to carry out programming before Purdue even had a computer of its own. So this would have been like back in the 50s, presumably, or maybe the early 60s. So back then, programs were written on like punch cards that IBM used all the way up until the early 80s. So what would happen is they had this one guy who was a driver/operator, and what he would do is at the end of each workday, he would go to everyone's offices and gather up their programs that were written on these punch cards, probably in an assembly language. And then he would take all the user programs and drive to the University of Chicago, and he would run the programs on their computer. And then he would gather up all the output and drive back, and then he would just go to everyone's office in the morning and distribute the output to them. Can you imagine if you made a little mistake, like the kind of mistakes that we all make in coding, that's how semicolon, dang it, whole day's work lost. So you have to be really careful. And most people pay attention to the fact that it's more efficient to multiply by 0.5 and to divide by 2, because as I mentioned, division is a bit more expensive than multiplication. So they knew all the tricks as to how to get the most out of what limited computing power they had. But now, because of the development cycle is so accelerated, and the computers themselves are so much more powerful, now it's like, I'll just try this, and oh, I messed up. Okay, do it again, do it again. And the thing is, a lot of the knowledge from those days about what led to the most efficiency, because it's really needed, it can be forgotten. There's a lot of like institutional memory there. And the thing is, what if that could make a difference? What if something can be made like even 10% faster? Because take like the biggest energy companies like Chevron, Shell, they perform simulations of like operations in oil reservoir engineering. And even though they can afford the best computers out there, their simulations can easily run for over a month, one simulation. So we really have to get it right. And it's important that to do everything as efficiently as possible. I read about how this one company that's in the gaming industry, they developed their own method for computing x to the minus 1/2. Now, I mean, programming languages all provide a way of computing x to the minus 1/2. I mean, they implement exponentiation, or they all have square root functions. So it's not something that wasn't there already. But they still developed their own method for computing x to the minus 1/2. That function in particular, because they wanted to get a little edge and have their gaming graphics and so forth perform more efficiently. Then you have to be wondering, why x to the minus 1/2? What's so important about that? Well, if you have a vector, you compute the magnitude of a vector, square root of x squared plus y squared plus z squared. And then you normalize the vector by dividing by that magnitude. So you have to multiply the components of a vector by magnitude to the minus 1. The number raised to the minus 1/2 power to normalize a vector. So, and that operation for graphics is performed all the time. So they developed their own method. And some of the tricks, the techniques they use in their method are ones that we will learn about at the end in this class, toward the end of the semester. I wasn't planning to talk about all that. But I figured it'd be good to have some perspective on how times have changed, and why we pay attention to every little operation. The people who develop certain algorithms went to a lot of trouble, even if they had things worked out correctly as far as the exact arithmetic was concerned. Like it's sort of that would satisfy the kind of mathematician who wouldn't really care about efficient implementation. But we still need efficient implementation. A lot more work still has to be done. And that's why in homework 3, you're dealing with coming up with a second quadratic formula. Make sure that quadratic equations can be solved as accurately as the floating point number system will allow. Am I getting my notes? I'm not getting my notes. Okay. Yeah. I won't get into this here, and it's not something related to a homework or midterm, but what I've shown you here for efficiently evaluating the Newton form is called nested multiplication, and it's this algorithm 7.3.5 in the text. But nested multiplication is mainly used to evaluate the Newton form efficiently, but it has another use. That if you apply nested multiplication to the Newton form of your polynomial, n times, where n is the degree, by plugging in x equals 0, you can actually use that to convert the Newton form to a power form. And there's an example in the text that shows how that's done. Okay. So now that I've covered that topic pretty exhaustively, but as far as midterm is concerned, well, actually, I can go ahead and open that up. Okay, this is a practice one. So this is what's already posted in Canvas. But just to give a sneak peek. Okay, yeah, so one of the questions is, okay, here's a function, EVX, and you come up with a third degree Newton interpolating polynomial where these 4 interpolation points, the x values are specified. So then the y values would just be f evaluated at the x values. Oh, hold on. Okay. Oh, shoot.
What happened?
No, I'm gonna have to review this. Well, not only this practice exam, but the real exam too. Okay. In this question, question 4, as well as question 5, there's part of the question deals with the error in the interpolating polynomial here, and also here. That's in section 7.4, which I just said will not be in the midterm. So it's a good thing I looked at this now. Because I don't cover that till after the midterm. So I'll fix this. And I think I might have already exercised it for real tests. I just hadn't done that for practice. So don't worry about that. Okay. So for divide difference, again, you're filling in the divide difference table, and then in this case, like using, for example, the top row of coefficients to construct the Newton form. Okay, so that's the sort of thing that's relevant from this section covered today. Oops. That's the most important part. Yeah, I think, yeah, when I taught this class 2 years ago, I actually didn't cover 7.4 and include on the midterm. And I think schedule-wise, because of timing of fall break, it just turned out to be too much of a hassle. So I'm like, okay, I'll just cover less. So, whoops. Okay, well, I'm glad I wrote that over this because you all have been looking at all this. Like, hey, you're trying to test us on something that you haven't covered. Yeah, I would not knowingly do that, but I almost unknowingly did it. Okay. Oh, by the way, I mean, I'll mention this later because on Tuesday, next Tuesday, I'll be going over this. Taking any midterm related questions. I mean, for the homework, it's a good thing, for you all to, collaborate with each other or ask me questions. I'm pretty freeform about that because I figure that's how the most can be learned for the first time you all see this material. The midterm and final, though take home, is a different story. I expect an independent effort. And for those 2 items, the only questions that I will take are ones that involve clarifying the question, making sure it's understood what's being asked for, but then I can't go beyond that. So to make sure I'm clear about that. But also, I know the temptation's out there, and people might try to see what they can get away with. I expect not to be collaboration on those 2 things. And if in a situation where I see identical work, especially identical flawed work, tends to stand out more, I will notice, and it's going to be a problem. so just don't do it.
Sorry, what?
On the take home midterm and final, even over take home, you're not supposed to collaborate with your classmates. It's supposed to be carried out independently. So I just want to make sure that everyone knows that. So, I mean, whereas homework, go ahead and talk to your classmates about problems, it's perfectly fine, but not for the midterm and final. So those are ground rules.
But for the practice midterm.
What?
For the practice.
What about, that's not an assignment.
I know, but it's still,
If you have questions about it.
yeah.
Considering it's not even a graded item, you can ask all the questions about that if
Okay,
you
well,
want.
I don't know. Like, it's essentially a practice midterm, so.
Well, yeah, and I know that by that, putting it out there and giving you all substantial advantage, but I figure the problem might be painful enough anyway.
So we can, because you said, next Tuesday we're gonna go over, like, any questions about practice midterm.
Yes, yeah, that's what that class is for.
Like, we only ask clarity questions? I was confused by that.
Oh, I meant the real thing. But what we're hoping is because it's a practice, that questions of real thing we clear out. It looks like I got some editing to do. Okay. I think I let something like that slip through, but I guess if I changed things from the last time I taught the class, then that's not what happened. Anything about error, like, okay, so I can't put it on the midterm, but you can expect it on the final. Which will have a similar format. Okay. Other questions about anything? Homework, quizzes, midterm. Almost done all over. Oh. Is there something, or is there a question? Well, I'll stop recording anyway.
Can't even look at